All right, welcome to class. Welcome to section 5. We're going to be talking about downhole pumps and pump operation and rod operation in this section, and it's going to be a very important section here, so I highly recommend that you stay with me and do not jump ahead already to the dynamometer card interpretation, because we're going to learn a lot of things here and build on it in the next section, but also some of the most important principles of understanding rod pumping systems are going to be here in this section. So let's go ahead and jump in and see what we're going to look at here in the overview. Well, we're going to talk about downhole pumps, how they work. We're going to look at valve action. We're also going to look at some different variations of downhole pumps. We're going to look at balls and seats for our traveling valve and standing valve, and we're going to look at valve action. What causes the ball to be on the seat, and why does the ball sometimes come off the seat? Okay, as fluid is moving through it. Well, that's due to the action of the plunger moving up and down, creating different pressures here in the pump chamber. But we're going to look at valve action. We're also going to talk about slippage, look at a slippage equation, and we're going to calculate displacement for a rod pumping system if you have your main pumping parameters. And what we're going to do a lot in this section, and probably more so in the second half, is we're going to look at this in the first video here as well quite a bit. We're going to look at the fluid load. Okay, what is the fluid load? Okay, well, the fluid load, this is the weight that is being borne by the plunger, and the rod string is picking that up here on the upstroke, as we see here in our downhole card. So we're going to talk about the fluid load, what it is, what affects the fluid load, and then we're going to see how the fluid load affects rod stretch, or how it creates rod stretch, which is taking away downhole stroke length as the rods pick up the fluid load. And the rod stretch will be evident on the surface card. Okay, you see rod stretch on the surface card, not the downhole pump card, and there is a helpful constant here, notice the rod spring constant, that will line up with our surface card if the conditions are right. It's a helpful load reference line, but it basically relates to how stretchy the rod string is and how much the fluid load is stretching that particular rod string. So the fluid load is on the plunger and rods on the upstroke. On the downstroke, it is going to be on the tubing. And if you don't have your tubing anchored and tensioned, you're going to have tubing stretch. And that is something you can see down here in the downhole pump card. And the downhole pump card will slant on both sides. And it's also going to slant at a constant, and it's going to be the tubing spring constant. Okay, so we have these two helpful load reference lines right here, but we're going to talk about these in conjunction with rod stretch and tubing stretch. Then we're going to quickly look at rod loads in the system. We'll go into more detail in the second dynamometer section on this. We're going to calculate the downhole stroke length. Very important to understand what factors go into it. And then we're going to look at stress waves. Okay, so if you have an impact like this tag that's traveling up and down that rod string, how those stress waves are interacting and how they're moving up and coming back down, kind of like repeats on a fluid level shot. So let's go ahead and jump in. Now, the downhole pump is the heart of the rod pumping system. Everything is about operating the downhole pump. We've got a big pumping unit surface. We have this long rod string that's connected down here to our plunger. So this is a little miniature plunger right here. Here is the traveling valve on the bottom of the plunger. And here is the standing valve, which is a part of the bottom of the barrel assembly. But as I start this video here, this is what the whole system is about, because here we're displacing fluids. Fluids are being sucked in from the annulus. Okay, so here on the upstroke, they're being sucked into the pump chamber. It closes, and then it gets compressed and pushed above the traveling valve and plunger. So fluid sucked in, compressed, and then discharged above the plunger, and it's going to progressively make its way up the tubing all the way up to surface to our tank battery so we can sell it. So here's another video, and this one's basically the exact same thing, a couple differences. It does show us the ideal downhole pump card, and you're going to see as I start this video that it's going to rapidly pick up the fluid load. Okay, remember this is the load here on the y-axis. It's going to rapidly pick up the fluid load, and then the plunger is moving on the upstroke. This is the position of where it is on the stroke on the x-axis. So notice it rapidly picks it up, plunger's moving up, and then it's going to release the fluid load right there, and then the plunger moves back down. Now notice on the upstroke, what I kind of like about this video is that the fluid level is dropping in the annulus on the upstroke, because that's when fluid is being sucked into the pump chamber. And then on the downstroke though, the fluid level is rising because it's not sucking new fluid into the pump chamber. But basically this is what's going on right here. We're going to look at the valve action related to what causes those balls to come off their seat as the plunger is moving around and it's stroking. So we've already kind of looked at the pump components, but a quick review right here. We're going to look at some different style pumps in this section, but we have our barrel assembly and our plunger assembly. There are different types of pumps. I'll show you those coming up. This is going to be an insert bottom hold down pump right here. But if we look at the main components here on the barrel and plunger assembly, we have the barrel and then the plunger. And of course, the plunger is going to be inside the barrel, and it's the tight fit between the plunger and the barrel that's holding the pressure differential, and then also in conjunction with the traveling valve. All of that is the seal assembly that is holding the fluid load. So the barrel, the length of this is going to be dependent on what the downhole stroke length is. If you have a very long downhole stroke length, you're going to need a longer barrel. The length of the plunger is going to be dependent on the pressure differential acting across it. So if the pump is set shallow, you might only need a 2-foot plunger. If your pump is set very deep, say 10,000 feet, you might need a 5 or 6-foot plunger. You need a longer seal section because there's a greater pressure differential acting across that plunger that's going to try to lead towards slippage. So these are the main components here. We have our traveling valve, of course. This is going to open and close based on the movement of the plunger. It's called traveling because the plunger is attached to the rod string, and so it travels up and down with the stroke length of the pumping unit. Down here on the bottom of the barrel assembly, we have our standing valve. And this is going to be our check valve at the bottom of the tubing to prevent any fluid from leaking back down through the pump and getting outside or going back down into the annulus. That would mean our tubing is draining. We don't want that to happen. And our standing valve is called standing because it does not move up and down with the stroke length. So, of course, there's different metallurgies and some different things you can do with the plunger and the barrel. We'll talk a little bit about that in the gas and solids separation section. Some other main components. We have a valve rod guide that is right here and a top discharge. This is where the fluid is coming out here on the top. So the valve rod guide is just to try and keep the valve rod centered on the inside of that pump. So the rod string is going to connect right here to this top connection, and then it connects to your valve rod, which comes down to your plunger. And then we have the hold down right here. This is going to be set down in the seating nipple. So this is also another place where fluid could leak out of your tubing. Fluid could potentially leak if you had some leaky valves down through the standing valve and out of your tubing, but also fluid could leak around the outside between the ID of the tubing and the outside of the pump around the hold down here if this was not properly sealing, excuse me. So anyways, these are the main components. Now keep in mind that our plunger is hollow, so fluid is moving up through the traveling valve, up through the hollow plunger to the top. Of course, that's in here, and then it's going to come out the top discharge right here. So our valves, our standing valve and traveling valve, they look like this. It's just a ball on a seat, and here's what valve seats look like. Okay, it's just basically like a donut. It has a little beveled edge that's going to create a tight seal with that ball when the ball is sitting down on top of it, assuming that the ball is in good condition and assuming that little beveled edge is in good condition and it's not corroded. Here's an example of a bad seat. Okay, this is going to be washed out right here. You can see that there's a spot. It's not going to create an effective seal when that ball is sitting down. This is washed out due to fluid erosion. So that's not going to create an effective seal right there. Now our ball and seat are going to be in some sort of cage to confine them, so they're just not floating around everywhere. And there's different types of cages. This is an insert guided one. It tries to kind of guide the ball off the seat and back onto it so it doesn't rotate around or vibrate around so much. There's also balls that put a vortex spin on the fluid to try to minimize the ball chatter so it's not banging around on the cage to damage the ball or the cage. But basically it's going to be in some sort of cage. Okay, now this is the main components of your downhole pump, and the ball and seat are extremely simple and they have not changed in a long time. This is pretty much what you're always going to see. But I was reading an old paper, okay, that was from the 1960s, and it's referencing some older time earlier in the oil industry, and I thought it was fascinating because it was talking about the ball and the seat and what it was made out of. And let me just read this for you right here. It says, "The heart of an oil well pump is in the valves. The valves used in the pumps in the relatively shallow wells in Pennsylvania were made of brass and leather. The leather was attached to a bronze drop with a screw, the leather seated against a smooth surface of a seat, and provided an effective seal. The very best grades of leather were used in the early valves, and at shallow depths did a very good job." So they're talking about using bronze and leather as valves. Well, if you have a very small pressure differential, I have no idea what depth these wells were at, but maybe they were at 1,500 feet, something like that. Then maybe that would work well enough. Obviously, it's not going to work as well or be as durable and last up as long as it would if you have a steel ball and seat. So anyways, kind of interesting to see that there. Now, what's important about the ball and seat is that they're one-way check valves. And we know about check valves from the fluid level shot section, right? They're designed to only let fluid move in one direction. So in this image right here, it's only supposed to let fluid move from left to right. If something wants to go from right to left, this flapper is going to seal right here and prevent it from backflowing. Okay, so that is a check valve. Well, that's what the balls and seats in our pump do. They are check valves. They're designed to only let fluid move their way vertically through the system. Okay, and so they're going to naturally fall down on their seat, and they will be closed if anything wants to flow down from the top going down through the bottom here. So they're going to be closed when we look at valve action if you see a ball sitting on the seat. Now, if you see a ball come off the seat, the reason that it's doing that is that fluid is flowing by that ball. That's the reason it's coming off the seat. And why is fluid moving by that ball? Okay, the only time it's going to do that, the ball will only come off the seat if the pressure below is greater than the pressure above. So if the pressure down here is greater than the pressure here, fluid's going to move through that valve, that ball and seat, and it's going to come here to the top section of it. But then if the fluid wants to flow back down through it, it's going to be a check valve. And it says, nope, you can only go one direction. We only want fluid to migrate its way up vertically through the pump and up the tubing to surface to our tanks. Okay, so keep that in mind, that they're just one-way check valves. The only time they open is if you create a pressure down here a little bit more than the pressure above. The fluid's going to flow, and it's going to push the ball off the seat. Okay, so let's look now on a high level as to what's happening in a rod pumping system. So we've got two different pressures on both sides of the pump. Okay, on the bottom side of the pump, the fluid that's being sucked in is at the pump intake pressure, and that just means the fluid is at the pressure here at the intake. Okay, in order to calculate what the pressure is, you would take the surface pressure plus the pressure of all of these columns and add that up. So that is the pump intake pressure, and in this illustration here, it's going to be low. And the pump has to take that low pressure fluid and compress it to the pump discharge pressure. And of course, to calculate that, you would take the tubing pressure and then you would add up what is the pressure due to this gas and water column right here down to the bottom of the tubing. So it's taking in fluid at the pip, and it has to compress the fluid to the pump discharge pressure. So it has to act like a compressor. And the pressure differential and the diameter of the pump, this is what is creating the fluid load. We're going to talk a lot about fluid load. Remember that it's abbreviated F sub O. So the fluid load, this is the equation. This is our new favorite equation for this course right now. Okay, the last favorite equation was how to calculate the distance by using the round-trip travel time when we were looking at fluid level shots. This is our new favorite equation. Write this equation down. Okay, so the fluid load is equal to the pressure differential acting across the plunger times the area of the plunger. And what is the pressure differential? Well, we have that pressure up here, the pump discharge pressure, and the pressure down here is going to be the pump intake pressure, at least the minimum pressure that's experienced below here. Okay, there's going to be some varying pressures occurring down here in the pump chamber, as I'm going to show you here. But it is the shape of the cards. When we look at a downhole pump card, what we're going to look at in the next section, okay, the downhole pump card represents what the load is versus position on the pump plunger. So as the plunger is moving around in the stroke length, what is the load on it at all points? Okay, so you can see that this is the full fluid load. Once we get to this top flat line, the full fluid load is on the plunger, and down here there is no fluid load on the plunger. Okay, but every point on this card represents what the fluid load is. So here at the start of the upstroke, as the plunger just barely moves up a little bit, now it's picked up about a third of the fluid load. And here it's picked up about 4/5 of the fluid load. And here's the full fluid load. But every point on these cards represents what the fluid load is based on this equation. Okay, and this is a very important slide. Try to pay attention, and this might be a little bit advanced, but at least let me plant the seed. I'm going to come back to this in the next section, but this is kind of the secret to interpreting dynamometer cards right here, very high level. So when you look at the area or the volume between our traveling valve and our standing valve, this is our pump chamber. Okay, this is where fluid is sucked in at a low pressure and it has to be pressured up. And of course, this volume is changing. If this is your standing valve and traveling valve, as it's stroking up and down, the volume between those valves is shifting. But as the plunger moves up and down, it's causing different pressures to occur here in the pump chamber. And this is going to affect, basically, let me just say that the shape of the dynamometer card is basically dictated to the greatest degree. There's a couple other factors, but to the greatest degree by what the pressure is in the pump chamber. Okay, and so what the shape of the card showing you in this particular case, it's basically just showing you what the pressure is in the pump chamber. And let me show you how that is the case. So if I take this equation and I expand it out, okay, the pressure differential acting across the plunger, well, we have the pump discharge pressure here, and down here we have the pressure in the pump chamber. Okay, this is the pressure differential acting across it times the area. Now, when you look at this equation, the only thing that's changing from stroke to stroke is what is the pressure in the pump chamber. Okay, and this is what's changing in the middle of the stroke, okay, as the plunger is moving up and down. The pump discharge pressure is staying approximately constant, right? You have a column of oil and water, and then you have a tubing pressure here, so you have the same pump discharge pressure. The area of the pump is staying constant. That doesn't change until you replace the pump with a different diameter. What is changing is what is the pressure here in the pump chamber, okay? And so this equation, looking at the fluid load, is what's dictating the shape of the downhole card. So for example, on these cards here, these were fluid pound. It's a series of cards where initially it has 100% fillage. Fluid load's released nearly immediately, but then some of these panhandles start to form right here. Now, why is that the case? Well, on the upstroke, the fluid load is being held, and in the fluid pound case, it continues to hold the fluid load on the downstroke, and then eventually the fluid load is released. Okay, and what this indicates, since it's still holding the fluid load as the plunger's moving down, that indicates as the plunger's coming down, it's not pressuring up the pump chamber until eventually it gets that gas compressed to a small enough area, and then it pressures it up the pump chamber. Okay, and once we get down to zero fluid load on the plunger, okay, if you look at this equation, if you plug in a 0 right here, the fluid load equals 0 times the area. Well, that equals 0, and that's where we're down here on the 0 load line. Okay, so hopefully that makes sense. It is the pressure in the pump chamber that's dictating the shape of the card, and we're going to talk about that in more detail. So in this section, we're going to talk a lot about fluid load. And what is the fluid load? Well, I just showed you an equation for what the fluid load is, but let me show you a visual way of thinking about what it is. It is the load acting across our plunger, but imagine if you had a pumped off well, okay? And let's look at what the tubing looks like. So in these illustrations, the blue here represents what the diameter of the tubing is, and the green column right here represents the diameter of the plunger. So we've got, I don't know, let's just say we have 2 7/8 tubing, and then we have an 1.25" plunger. And in this one, we have our same 2 7/8 tubing, but we have an 1 3/4" plunger. Okay, so look at the volume of fluid that is above the pump. This basically represents what the fluid load is, because the fluid load is, and this is another way of thinking about it, it's equal to the volume of fluid that is above that diameter plunger. So from down here where the seating nipple is up to surface, okay, that volume, it's going to be more volume if you have a larger diameter, makes sense. But you take that volume of fluid times the density of that fluid, and that's basically the load, the fluid load that is being picked up by the pump plunger. Now, what about this case though? Okay, this was a pumped off well. Okay, now we have a lot of pressure support from a high fluid level here on the backside. Remember we were talking about net lift? Okay, net lift would kind of be like from this point up. That's where the pump feels like it is lifting the fluid from. Well, if we looked at this scenario, again with an 1.25" plunger, this is what the fluid load would be, approximately. This is not exactly true. There's some caveats I could throw here, but for the most part it is true. But this is what the fluid load would be. Notice there's less volume. Okay, you might have the same density fluid, but you have less volume because we're getting pressure support. So our net lift is shorter, but that's basically a way of thinking of what the fluid load is. Think about a cylinder from that pump going all the way up to surface when you take into account the net lift. Okay, and that's basically the fluid load That's the fluid that has to be picked up by that plunger each upstroke, and of course the rod string are going to bear that fluid load as well. So here's one more video on how a downhole pump works. Okay, and we're about to go look at the valve action in the next slide. And this is at the Petroleum Museum here in Midland. I just took my wife's parents to go visit it, and they have this nice model where you can stroke a little pumping unit up and down and see what's happening downhole with our valves. Here's our standing valve, traveling valve, and this is our plunger right here. And I said, hey, really cool. And I asked my wife, go ahead and stroke it and let me make a video. And you know, women, they just don't know how to stroke a pumping unit. I said, sweetie, you're not doing it right. You come hold the camera and let me stroke this thing. And I started stroking it real good. So look at this. So what I'm doing here, and the way I wanted it done, was to kind of pause it here at the top and bottom of the stroke so you can see. So on the upstroke, standing valve opens, fluid fills the chamber, and then it comes down. And as it comes down, that plunger is compressing the fluid in the pump chamber. Okay, so it's sucking in fluid, trapping it, compressing it. Okay, it's going to suck in fluid, and it's going to trap it and compress it. And we're going to see why the valves open now on this particular slide. So let's look at valve action, and we're going to use diagrams like this, and we're going to use this ideal pump card right here. So remember, when we look at the downhole pump card, we haven't talked about that yet. That's in the next section. I'm sure most of you are familiar with it though, but this is the load on the y-axis, and here's the stroke length, the position. So we're going to start off at point 1 right here where there's no fluid load on the plunger, and we're at the bottom of the stroke. So we're idle at the bottom of the stroke and both valves are closed. So starting at the bottom of the stroke, the plunger was just coming down from the prior downstroke, and as that plunger is coming down, it momentarily pauses before it starts to move back up on the next upstroke. And that's where we are right here at point 1. And so as the plunger starts to move up, okay, it's going to pick up that fluid load, and that's what this card represents. It picks up the fluid load, and then we get to point 2. At point 2, the full fluid load has been picked up at this particular point, and you can see in the diagram that the plunger is a little bit higher. Okay, so as the plunger is moving up, it's vacating the pump chamber. It's creating additional space, and this is going to drop the pressure here of the fluid in the pump chamber. So the rods in the plunger are picking up the fluid load. The standing valve opens when the pressure inside the pump is less than the pump intake pressure. So if we look at the pressures that we were talking about, pump discharge pressure, pump intake pressure, here's the pressure in the pump. Okay, the standing valve is going to open because the plunger is moving up. It's dropping the chamber pressure by vacating or creating more volume in this space right here. And once the pressure in here becomes less than the pressure here, the standing valve opens. Another way of saying that is once the pressure here is greater than the pressure there, you understand the standing valve opens and fluid starts to admit from the well, from the annulus. Okay, so from point 2 now, so at this point we have the standing valve open. Okay, and we're just started the upstroke. You can see we've just barely moved on the x-axis. So maybe the plunger moved up 1 inch. And now it's going to move up the rest of the upstroke. So for the rest of the upstroke, the standing valve is going to be open and fluid is admitting into the pump chamber. And then we get to point 3. And at point 3, this is the very top of the stroke for the plunger. And once the plunger stops moving vertically up, it's not going to create that lower pressure zone here in the pump chamber. So the pressure in the pump is now going to equal the pump intake pressure. So the pressures across the standing valve are going to be equalized, and therefore the standing valve is going to get closed. Or excuse me, it's going to close. It's going to fall down on its seat because there's no reason for it to be off the seat. There's no fluid that's moving in there because the plunger stopped moving up. At this point right here, this is when the fluid that was getting sucked into the pump, who thought, hey, this is pretty cool, look where we're going, all of a sudden the trap door closes, right? And that fluid that got sucked into the pump is now trapped. And it's got a closed standing valve on the bottom, and it has a plunger that's about to come down and compress on it to pressure it up. Right now, the fluid is at very low pressure, whatever the pump intake pressure is, but we have to pressure it up greater than the pump discharge pressure. So at point 3, okay, we start to move down, or the plunger starts to move down, and it moves down just a little bit, and it's releasing the fluid load. That's represented by the height of this green card. And you can see right here at point 4, we've released the full fluid load. And once that plunger moves just a little bit more, So it was here, and it moved down a little bit, and it released the full fluid load. Once it moves just a hair more, now all of a sudden the pressure in the pump chamber is going to be greater than the pump discharge pressure. And at that particular point, the traveling valve is going to open. Okay, and so now we started the downstroke. We've barely moved. Okay, we moved down just an inch, and now we're going to go down the rest of the downstroke, and our traveling valve is going to be open. So all the fluid that got sucked in is now moving. It's going to be moving here above the plunger. Really, I guess the plunger is moving down. And once we get down here to 0.1, you can see that the brown fluid we sucked in is now above the plunger. So as it's coming here, the traveling valve's been open, but once it stops moving downward, it's going to stop pressuring up the pump chamber. So what's going to happen here is that it's going to momentarily pause before the next upstroke. And what happens is that there's no pressure differential across the traveling valve, and the traveling valve is going to seal. Okay, so this is the valve action. This is what's causing the valves to come on and off their seat. And as we'll see with different cards, it doesn't always work this way, because sometimes you have low pressure gas getting in your pump, or even high pressure gas, and gas is compressible. So as you want to, for example, compress the fluid in the pump chamber, you don't have a vertical line here. You have a panhandle, because the plunger's coming down, but it's not pressuring up the pump chamber. And then eventually it pressures up the pump chamber. Okay, so we're going to look at basically, as I mentioned, it is the chamber pressure that's dictating the shape of the cards, as long as you don't have any noise or unaccounted friction or mechanical loads like tags occurring. It is the pressure in the pump chamber. Now, what's important about this is that we have a load transfer. Okay, the fluid load that's being picked up, it's on the rods, it's being picked up right here, and now it's fully on the rods and the plunger. And so in order to pick it up, there was a rod stretch that happened. You can't see it in the downhole pump card. You can see that in the surface card, but rod stretch occurred to pick up the fluid load. Then when you release the fluid load off the rods, where does it go? It goes onto the standing valve, and the standing valve is essentially a part of the tubing when it's stabbed down in the seating nipple, and that's going to lead to tubing stretch. We have this load transfer occurring. If the height of this card was 5,000 pounds, on the upstroke right here, the rods are carrying 5,000 pounds. And then on the downstroke, when the fluid loads on the tubing has to carry that 5,000 pounds. So there's a load transfer back and forth. It leads to rod stretch, and it will lead to tubing stretch if your tubing is not pre-anchored in tension. We're going to look at that. So let's look at the pump intake pressure and pump discharge pressure a little bit more, and highlight the fact that the pump is a compressor. Remember, it's taking in fluid at the pip, has to compress it to the pump discharge pressure. Here's a quick hydrostatics calculation just to get a feel for how you would know what the pump intake pressure and pump discharge pressure are. So if you had a 10,000 foot well, if we look in the casing annulus, we want to calculate what is the pressure of the fluid going into the pump. So we have a surface casing pressure, let's say it's 50 pounds. Okay, and then we have a column of gas right here. And in this example, it's 8,000 feet. An 8,000 feet column of gas, okay, with low surface casing pressure does not add up to much. It's only 18 pounds. It's almost negligible, right? It's going to be basically a rounding error in this calculation. So it's not much. If we had high casing pressure, that could be different. For example, if we had 600 psi up here, but that's not normal for a rod pumping well. And then here in this example, we've got 2,000 feet of oil, and you can calculate what that is. But we would add all this up, and that's going to give us a pump intake pressure of around 780. Okay, now for our tubing, in order to calculate the pump discharge pressure, we take the tubing pressure. So if you got a back pressure valve, let's say we've got 250 pounds on average on our tubing, and then we have our 10,000 foot column of tubing. We would have to look at what the specific gravity and the densities are for the water and oil in here, assuming no gas. And doing some calculations, it would come out to around 4157. So the pump discharge pressure, just rounding off, is about 4,400 pounds. So what is the pump doing? It's taking in fluid at 780. It has to compress it to 4,400 pounds. Now, if this well, we were able to get it to being pumped off, this column right here of oil would disappear. Your gas column would get 2,000 feet longer, and essentially your pump intake pressure, this might change to say 25. So your pump intake pressure would be 50 plus 25. It would be 75 psi, and it would still have to compress it to that same high pump discharge pressure. Okay, so remember, the pressure differential and the diameter are creating what the height of the card is. This is our fluid load right here. And notice on some of these cards, it's the same fluid pound cards, that we have some compression issues occurring here. So the pump is a compressor, but we don't want to get gas in the pump. We want to separate the gas out. Okay, and if you get gas in the pump, either due to pounding fluid, if there's not enough liquid to fill the pump chamber and you suck in gas from the annulus, you have gas in the pump. Or if you have gas interference because you're not properly separating the gas out before it gets into the pump, it can lead to compression issues, which is going to be an inefficiency in our system. So let's look at the fluid load here. Okay, fluid load equals area times pressure differential. We can all calculate the area of a circle with this equation. We know what the pressure differential is acting across the plunger, and this is actually the maximum pressure differential. Okay, because when you're looking at it, you want to actually look and see what is the pressure underneath the plunger. Well, the maximum pressure differential is if the pump intake pressure is what the pressure is beneath the plunger there. So the larger the diameter and the larger the pressure differential, the higher the fluid load. So let's say you had a well and it just had a failure and it's got a high fluid level, and you go and shoot it right after they put it back on production. You might find the top of the fluid level right here, and your dynamometer cards look like this, very skinny. Now let's say you come back a week later and the fluid levels pump down quite a bit. Okay, what is the dynamometer card going to look like? At that point, it's going to be a taller card because we have higher net lift. The pump now feels like it's lifting fluid from this point up to surface. Well, if you come back a month later, you've got the well pumped off. Now your dynamometer card might look something like that. Okay, so the height of the dynamometer card represents what the fluid load is on the plunger, and the fluid load increases as we bring that fluid level down. So notice as the fluid load increases here, there's more rod stretch. So initially our downhole stroke length was longer, and that downhole stroke length is going to shrink as we have more rod stretch, which is based on what the fluid load is acting on that rod string. So our downhole stroke length increases. So in this case, you might have been making 300 barrels of fluid per day when it had a very high fluid level. And then once you got the well pumped down and it's fully pumped off, even if it's still running 100% of the day with 100% pump fillage, it's not even pounding fluid yet, you might now only be making 200 barrels of fluid a day. You lost 100 barrels of fluid per day because your downhole stroke length changed. Okay, and it can even be more extreme than that, just depending on the circumstances. Now, notice you'll have more tubing movement as well if your tubing is unanchored in this particular case when it's pumped off. Why? Because the height of the card is higher. There's a higher fluid load transfer. And remember, that fluid load transfer is going to cause rod stretch, and it's going to cause tubing stretch. So let's look at downhole pumps here and just the broad categories of downhole pumps. We'll look at some of these throughout the course, but there are two categories of rod pumps. Okay, kind of broad, high-level categories. There are insert rod pumps, and then there are tubing pumps. So we've seen the insert pump. This is the most common. It's the image that I've been showing to you again and again, and partly because I have just one really nice image of this, and I don't have a lot of other nice images like this of other downhole pumps. But here's what an insert pump looks like. So we have our casing right here. Here is our tubing. And an insert pump is ran in fully, both the plunger and the barrel on the bottom of the rod string, and it is inserted into the seating nipple. Okay, and it's called an insert pump because you insert the whole pump. Okay, you run it all in on the rod string and you insert it here on the seating nipple. Now, a tubing pump is different. Here's what a tubing pump looks like. Notice on the tubing pump that the barrel now is attached to the bottom of the tubing string. So with an insert pump, it's on the inside of the tubing. Okay, with a tubing pump, it is screwed onto the bottom of the tubing string, and then it's only the plunger that is ran down in on the rod string. And the only reason that you would run a tubing pump is if you need a larger diameter. So with an insert pump right here, you can see that the plunger is limited. It has to fit inside the barrel assembly here, and then the barrel assembly has to fit inside the tubing. But if we were to take that barrel and we were to screw it onto the bottom of the tubing, now we can have a larger plunger. So that's the main reason that you run a tubing pump. Okay, but it has downsides to it because if you want to get the barrel out to refurbish it, maybe your pump barrel is worn, you're going to have to pull the rods and the tubing, as opposed to an insert pump, you can pull it all out on your rod string. So the largest insert pump plunger that you can run. So we're looking at our insert for the main common types of tubing. If you have 2 3/8 tubing, the largest diameter you can run is 1.5 inch. So if you had 2 3/8 tubing and you want to run an 1 3/4 plunger, you're going to have to use a tubing pump because you cannot fit the barrel in 2 3/8 tubing for an 1 3/4. Now for 2 7/8, you have more leeway here. You've got more room to work with, and you can run up to a 2-inch insert pump inside 2 7/8. This is part of the reason that 2 7/8 tubing is quite a bit popular. Well, not the only reason, but one of the reasons. You can get larger pumps down in it. And now when you look at insert pumps, this used to confuse me. Okay, so we have these two broad categories. Now there's some differences or variations you can have with insert pumps, but it's really quite simple. First off, it's where's the location of the hold down? Is it a bottom hold down like we see here, or is it a top hold down? And the second thing is what is moving. Okay, usually it's the plunger that's attached to the rod string that's stroking, but you can also have a traveling barrel pump. I will show you on the next slide. But if you understand that, insert pump, tubing pump, and then when it comes to insert pumps, okay, where's the hold down and what's moving? That's basically all the different types of pumps. Now, when it comes to tubing pumps, there's also oversized tubing pumps, and I'll show you that later on in the course. Now, when a well is tagging, what's actually hitting? So, for example, if you're tagging down like this, what's actually impacting on the particular pump? Well, when it's an insert pump, it's going to be the bushing on top. This is also known as the clutch. Okay, so it's going to be this bushing right here that is impacting the top of the pump. So when a pump is built, the valve rod is cut to be short so that your traveling valve does not impact your standing valve. Because if your traveling valve and standing valve are impacting, and you break a cage, you break your pump. And if you break your pump, you're going to have a rig out there to service it. So they cut it to where it's actually impacting right here on top. This is known as the clutch, and it's something you can use if you need to back your rod string off. For example, if your pump is stuck in the seating nipple, you can engage that clutch and set down some weight and try to turn the rods to the left to unscrew down there at the pump. But this is what's actually hitting right here. This is one that's beat up pretty good. And if you have a tubing pump, though, what's actually hitting is the standing valve on-off tool. Okay, and it's like the valves are hitting. So if you look at this illustration here, these little blue boxes, I didn't know exactly how to draw this. This is the standing valve on-off tool. So what that looks like, it's just something that goes on the bottom of the traveling valve assembly, and it's basically a big screw. So you've got fluid ports that are coming here to feed the traveling valve, but you've got a big screw down here that you can screw into the standing valve if you want to remove the standing valve and pull that out a hole, or if you want to drain the tubing, you can get down there and screw onto it. But if you have your pump spaced too low, with a tubing pump, what you're actually doing is this standing valve on-off tool is hitting the standing valve cage right here, and you're probably going to smash up this screw, and you're not going to be able to use it to screw in. But also potentially you could break one of your valves. It's a much harder impact on your valves than it is on an insert pump. So if you have a tubing pump that's tagging, you want to be more cautious with it. It's more likely to break than if you have an insert pump. Keep that in mind. So this is the most common type of pump right here that we're going to be looking at most of in this course. So it's going to be an insert bottom hold down pump. And let's look at types of insert pumps right here. Well, we have our bottom hold down. Okay, same image again. I know. All right. So what is a bottom hold down? Well, this is where it goes down on the seating nipple. That means that the barrel is sticking up inside the production tubing. And due to that, it's got pressure support. So that high pump intake pressure that you're trying to pressure up the pump chamber to on the downstroke, it also has that pressure on the backside. So it's not likely, you're not going to have issues with your barrel bursting like you might have if you have a top hold down pump. And so a top hold down pump, this is where the seating nipple is. And so the seating nipple is right here. So your barrel is sticking down out from your production tubing. So the pressure on the outside of this barrel is the pump intake pressure. And as a result of that, if you can't run these too deep, because when you're trying to pressure up the pump chamber, you have the potential of your barrel bursting because it doesn't have that pressure support on the outside of it there. Now, why would you run a top hold down pump? Okay, the main reason you would do it is if you have issues unseating your pump. So if you have a well that produces solids and even just small amounts of solids, if the pump's down there for a couple years, those solids will tend to accumulate here between the outside of the barrel and the inside of the tubing. And the next time that you want to unseat your pump and pull it out of a hole, you find that your pump is stuck. And so the reason you would run a top hold down pump is that you probably have a sandy well that produces lots of solids. It has to be shallower, probably less than 5,000 feet. Otherwise, you could burst the barrel. But in this case, you only have a couple inches where solids can accumulate. So it's much easier to unseat your pump for this particular style. So here's what a hold down looks like. This is a conventional style hold down here on the right. Okay, so I think this might be, I don't know, the way API recommends it, not exactly sure, but this is what you'll typically see. You'll see 3 cups if you have a cup type hold down. Okay, these are just some hard plastic rings. Basically, they create a pressure seal there in the seating nipple. And then there's also a no-go. Okay, and the no-go is termed no-go because the pump no-go through the seating nipple because of this. It has a lip that's sticking out to prevent you from knocking it down through the seating nipple. Okay, now this is a modified bottom hold down. I was sitting in on a presentation, I think it was from Oxy, I don't exactly remember, but they were talking about in their San Andreas field, they were having lots of issues unseating the pump. The pump was getting stuck, right, whenever they wanted to pull it out of hole, and that was expensive because they would have to back off the rods and then pull the tubing, and they started modifying their bottom hold down to try and get the pump to unseat better, and this is what they went to. They removed the no-go because due to the fact that you have this metal sticking out right here, that's good to keep it from going down through the seating nipple, but that's also good for solids to get wedged around it and to make it hard to unseat the pump. So they removed the no-go, and they also took off one of the cups. And they reported to have much better success in unseating their pump. Now, I don't know if there was any downsides to this, if they ever accidentally knocked the pump down through the seating nipple or anything like that, or since they only had 2 cups down here, did they ever have fluid leaking down through the seating nipple? I'm not exactly sure. But anyways, something interesting to think about. So when it comes to solids. So remember, when it comes to insert pumps, it's where is the hold down? Also, what's moving, right? Well, you can have a traveling barrel pump. Okay, now this is not normal at all. Here is the hold down. There is a hollow valve rod, and this is the plunger right here with the standing valve on top of it. Okay, now the traveling valve is right here on the barrel. And this is what attaches to the rod string. So this is going to scope over the plunger, and it's going to be stroking up and down. And the main reason that you would run this type of pump, these are not very common, is also due to solids and sticking the barrel. Okay, so that's kind of the main function for it, but of course it has some downsides and limitations as well. So you can have some different variations. This is an insert pump, top hold down, and this is the Harbison Fisher Sand Pro pump. There's a lot of companies that have pumps that are similar. Now notice this one has 2 different plungers, okay, and the way they sell this is for wells that make lots of sand production or maybe after a frac job. There is a top sand handling plunger. Okay, so you can see it's got these pressure actuated rings, which I'll show you here in a second. And then also it's got this lower pressure sealing plunger. So this is the sand handling plunger, the pressure sealing plunger. So basically this plunger right here is just trying to wipe everything clean and prevent any solids from getting down between this plunger and the barrel right here. That's what it's trying to do. So, and there's no pressure differential acting across this plunger because you can see there's some holes right here. So the pressure can equalize around it. So it's not feeling that force that would tend to cause slippage occur right there. So it wipes and it tries to keep this plunger in better condition to extend the life of your pump. So there's lots of things you can do where you can have different types of plungers, different configurations. Here's a very specialty type of pump. This is the Harbison Fisher variable slippage pump, and this used to be on patent. It came off patent, I think, in 2023, and now lots of companies are making these styles of pump. So what it is, it's got a normal type of plunger and a normal barrel on bottom, but then there's an opening taper to the upper part of the barrel here. And as that plunger moves up into this open taper, there's a huge clearance and the fluid load slips off. And the function of this is to compress the gas that comes into the pump. And so instead of compressing it on the downstroke, you're using the high pressure of the pump discharge pressure to cycle around the plunger and to compress all the gas that got into the pump chamber. So if you can't remediate gas interference by separating it out with a good gas separator, you might look at running one of these style pumps. Of course, there's limitations to this as well. Spacing is very important. You're pretty much going to need an all steel rod string for this to work. And these types of pumps create a unique type of card, okay? And it looks like this. So the fluid load, as I mentioned, the fluid load's picked up, it's carried, but it's released before the top of the stroke. This is the ideal card for a variable slippage pump. But some different variances you can have depending on what you're trying to attack. We're going to talk more about this when we get to the gas and solids separation and handling section. We'll talk about some different pump styles to deal with that. Let's look at pump slippage now. So slippage is going to be inherent. You have to have some slippage. This is where the fluid is slipping between the plunger and the barrel because you have to have some distance okay, between the outside of the plunger and the inside of the barrel in order for that plunger to move. But there is some advantage to slippage. It helps to lubricate and cool the plunger. So on the upstroke, when the fluid load is forming here across the plunger, and when the standing valve opens, now we have the full fluid load formed on it, because now we have the pump intake pressure here below the plunger. But when that happens, that pressure differential is going to tend to try and take fluid and have it slip down between the plunger and the barrel. And as we get here to the top of the stroke, you can see some of that purple fluid that was just level with the plunger is now slipped down beneath it. Okay, this is going to be slippage. You don't want too much slippage, but there's always going to be some slippage that has to occur. So the clearance, this is the term that is used for the distance between the plunger and the barrel. Okay, and it's in 1/1000th of an inch. It's also known as the fit, the pump fit. So if you're looking at what the clearance is, let's say you have a 1/6 clearance. Okay, that means there's 6/1000ths of an inch between the outside of the plunger and the inside of the barrel. That would be known as a 6-fit pump. And a human hair is about 4/1000ths of an inch in diameter. Okay, so if you had a 6-fit pump, that means you could take a bunch of human hairs and just kind of, put them right in there between the plunger and the barrel, and there would still be a little bit of room left. Now, usually when it comes to pump clearance and designing your pump, you usually have a 4 to 10 fit, and you try to approximately slip 2 to 5% of the production rate, but that's just kind of based on, it's completely dependent on the design. Okay, sometimes you might have designs if you have wells running super slow where they're going to slip a significantly larger percentage of their production. Okay, you don't want to have too much fluid slipping, that's inefficient, but depending on your design, sometimes you're not thinking about what is the slippage rate going to be for this particular well, or how much is it going to consume of the capacity of the system. And I'll show you some interesting examples of that coming in the next section. Now, if you have too tight of a clearance, okay, you can have plunger drag that can lead to buckling. So if your plunger fits too tightly with the barrel, it can lead to compression issues on the downstroke, especially for the rods right above your plunger there. It can also lead to solid sticking. Little solid particles can stick your plunger. And if your plunger clearance is too loose, we have our slippage inefficiency. So we don't want to be too tight or too loose. It depends on the circumstances. In solid slip too, so as the fluid is slipping down due to that pressure differential, any solids that are here in the fluid are going to also try to slip down and wedge themselves here between the plunger and the barrel. And you've probably seen many examples of plungers that are cut up, just scored here due to the sand that was being cut up as it was grinding between the plunger and the barrel. And if you get enough solids down in there, you can stick your plunger and it'll stop completely moving. So here's what a plunger looks like. This is a grooved plunger. Okay, the most standard type of plunger is just going to be solid uniform diameter all the way down, but it's quite common to run a grooved plunger that has a little groove cut into it about every 6 inches all the way down. And the function of this is that if solids get down here and they start to work their way down, they can come down to a groove right here and then hide out there. And it basically becomes like a little solid hotel, and they can hide there until that pump is pulled out of hole. If that groove is not there, they will tend to cut themselves all the way down until they're dissipated. Basically, they're smashed up into little tiny, flour, that sort of thing. But a lot of times with grooved plungers, you will see that the top section is cut, and then after that groove, everything below that looks significantly better. So I'm a fan of grooved plungers myself. Now, you can also have pressure actuated plungers. And this is a special type of plunger, not too common. It's not little grooves cut into it. It's got some big sections cut out, much more closely spaced. And inside there, you put some pressure actuated rings, which try to fold out on the upstroke. And basically, this is used for dirtier types of wells, from my understanding, but something else you can look into as well. And when it comes to slippage, okay, we can get an indication if there's a lot of slippage from a dynamometer card. But what you really want to do is you really want to try to quantify the slippage rate, and you can do that with a valve test. We're going to look at this in the second dynamometer section. What you do is you stop the unit on the upstroke, and you're measuring the load on the polish rod versus time. And when you stop the pumping unit on the upstroke by pulling the brake, you see how fast the fluid load slips off. Okay, so this is the fluid load slipping off right here, and then once it goes to a flat line, the full fluid load is slipped off. Here's another test. And the software will quantify for you what the actual slippage rate is. And let's look at the slippage equation, okay, the Patterson slippage equation. This was developed at the Red Raider #1. This is a test well at Texas Tech University, which is in Lubbock, Texas. This is just a couple hours north of Midland. And my understanding is that this test well is on campus here. And so they drilled a 4,000-foot well, they cased it, and they cemented it into place, but they didn't perforate anything. It's just a test well where you can run equipment down in there and do various tests. They have all sorts of instrumentation, that sort of thing in there. And there was a series of tests, I think it was 3 different tests that were performed over some period of time, I don't know, like 5-6 years, where the industry, I think it was ALRDC, was trying to quantify or come up with a good slippage equation. And so here is the actual well right here. So this is the casing for it. Here is our pump, and this is our tubing. So they had a different size pumps downhole. They had an 1.5 inch, 1.75 inch, 2 inch. They had various different types of fits between a 4-fit and a 20-fit, and they had a variable slippage drive. And I believe they had a 144-inch stroke length. That was constant. Okay, but all these other things, they were varying. And they were producing the well. It was coming up here. It was being metered. And then they were circulating the fluid back down hole. Okay, and so they were ensuring they kept a high fluid level so they didn't have gas interference, but they were adjusting things based on the pump size, the fit, how fast they were stroking it, and after a long series of tests, they came up with the $3 million equation. Okay, that's how much money they invested to come up with this particular equation right here, and this is it, to calculate slippage, the best equation that we have. So slippage equals... Okay, now if we look at these variables right here, first off, notice they found there's a dynamic component to slippage. So as the well is pumping faster, it has more slippage by the plunger, which is counterintuitive. Okay, and I'm going to explain that here a little bit more in a second. But notice there's a very small coefficient in front of the strokes per minute variable right here. So if you increase your strokes per minute from 6 to 9, okay, you're going to have more slippage, but that coefficient is going to dramatically knock it down. I'll come back to that here in a second. But let's look at the other variables, which are going to be more important here in affecting slippage. So first off, if you have anything here in the numerator, if you increase this, this is going to increase the slippage. If you have a larger diameter with everything else being held the same, you will have more slippage. If you have a larger pressure differential acting across the plunger, you will have more slippage. If you have a greater clearance or distance between your plunger and your barrel, you're going to have more slippage. And this variable right here is more important. It's raised to the 1.52 power. Okay, so this is all in the numerator. Now in the denominator, if you increase this, when you divide by a larger number, you come out with a smaller number. So if you increase the length of the plunger or the seal section, you're going to have less slippage. Makes sense. If you increase the viscosity of the fluid, if you're pumping a thick syrup as opposed to a low viscosity fluid, you're going to have less slippage. So if you're pumping heavy oil, you probably would have very low slippage. They probably run very big clearances for heavy oil. I don't necessarily know. But anyways, this is the equation right here. This equation's actually in the TAM software. If you output a PDF report and it tells you the slippage rate, it's basing it on this calculation, because in the software, it actually asks you what is the length of the plunger? What is the viscosity of the fluid? So anyways, the conclusions from this study, and if you want to look into it, here's the final paper they did in 2007. But their conclusions were that older slippage equations overestimated the slippage, and so operators were running a tighter fit than they needed to. Okay, now here's coming back to the strokes per minute. Increasing the strokes per minute will increase the slippage, which I think is counterintuitive. If your pump is slipping more, you want to increase the strokes per minute. It'll increase the slippage, but we got a big but. Okay, this is small in comparison to the increase in pump displacement. Okay, so it's still a good idea to do it, but they found in their testing, there is a static component to slippage, like the pressure differential and the clearance and that sort of thing, but there's also a dynamic component. So the faster they were stroking it, the more slippage they were actually seeing, and it was taking off a percentage of the slippage. But anyways, don't get caught up on that. But an important equation here to understand, and this is the minimum recommended fit that they have in that paper. So they're saying don't run anything less than that. Operators were running plungers that were too tight in their opinion, and you don't need to do that. So, and this is up to 8,000 feet, but if you have an 1.25 inch pump, they're saying you should run the minimum a 4 or 5 fit. Don't run a 3 fit, something like that, and you can see what the rest of the recommendations are. But anyways, kind of interesting to understand what components go into slippage. Now let's calculate production. Okay, we're going to do this very quickly. I know this is quite basic here, but I'm going to tell you an interesting way to think about how a rod pumping system is actually getting the production. Okay, so the barrels of fluid per day is equal to the volume being displaced, how frequently that volume is being displaced, or strokes per minute, how effectively it's getting that volume, and then the percent runtime. Okay, so kind of an interesting way to think about it. Here are the variables. I'm going to take you through it though. What is the volume? Well, if you have a certain diameter, okay, you can calculate the area of a circle, and then you multiply it by the downhole stroke length. That is the volume that the plunger is pulling up each stroke. Now the question is, how many times or how frequently is it doing that throughout the day? That's what our strokes per minute relationship is. And then how efficiently are we doing it? Do we have lots of slippage, or do we have free gas in that volume? And then what percent of the day are we doing it? Okay, so, and it's important that you use the downhole stroke length. Do not forget that. Some people just use the surface stroke length, but you might have 142 input stroke length, but you're only getting 70 inches downhole. And so you would want to plug this number into it when you're looking at this relationship. Now, this is not a true equation here because you need some conversion for units, and this is how you can actually calculate the production. Okay, there are two different equations here. One of them uses a pump constant related to the most common sizes of diameter here, and that takes into account, this equation with the pump constant takes into account the conversion and the diameter squared, but you don't need to use this. You can just use this top equation and follow the directions. So that's on page 1 of my rod pumping brochure. Okay, one more slide here before we end this video, and we're going to start talking now about the fluid load and rod stretch. We're going to pick it up with rod stretch in the next video, but let's do an example calculation on fluid load and see how the fluid load changes based on the diameter of the pump. So we have our model right here of our well, and let's say we have a 10,000 foot well. It's pretty common out here, and the well is fully pumped off. And if that's the case, your pump discharge pressure is probably going to be around 4,100 psi, and your pump intake pressure will probably be somewhere around 100 psi. We have pretty high line pressure out here, but just to simplify the math right there. So remember, on the upstroke, the fluid load is forming here. Once we pick up the full fluid load, our standing valve opens. Now we have the maximum pressure differential. We have the pump discharge pressure on the top. We have the pump intake pressure here on the bottom. We can use this equation to calculate what the maximum fluid load is. Our pressure differential is going to be 4,000 psi. The area of a pump is this equation. And let's look at what it's going to be as we vary the diameter of our plunger. So if we have an 1.25 inch pump, here's the area of that plunger, and here's the fluid load. 4,900 pounds. That's what it would be for our 10,000 foot well if we have a small diameter pump. Okay, and it's pretty common to see at 10,000 feet, if the well's pumped off, that you have an 1.25 inch pump because your fluid loads start to get quite high as you increase the pump diameter. Remember, fluid load is the height of the card. So if we look at some different scenarios here, let's just jump down to an 1.75 inch pump. Okay, with an 1.75 inch pump at that depth, now the fluid load is 9,600 pounds. Okay, quite a bit higher. And then let's jump down to something that's pretty ridiculous. You really don't ever see, very rarely, should I say, I've seen an 1.5 inch once at 10,000 feet, and it was with a very long Rotoflex style unit, long stroke length at surface, 366 inches. But if you had a 2.5 inch pump down at 10,000 feet and it's pumped off, your fluid load's 19,600. Let's just call it 20,000. That's a very high fluid load. And that high fluid load right there is going to create a lot of rod stretch. Okay, and so as a result of that, due to the fact that you have a high fluid load at that depth, you're going to need a strong rod string. And since you need a strong rod string, it's probably going to be larger diameter, and therefore you're going to need a very big pumping unit, right? Because now we have a heavy rod string and we have a heavy fluid load, and that's why you don't typically see these sort of diameters at that depth. Also, you would not be able to use fiberglass rods because fiberglass rods are so stretchy. With that fluid load, your downhole stroke length would be significantly reduced, and it would not be worth it to have that sort of diameter. We'll look at some examples of that in the next video. Now, let's say you have a pumper, okay, for this particular well, and he's a smart guy. At least he wants to apply himself. And he says, hey, boss, I think we're getting a little bit of gas interference. I'm going to crank up the tubing pressure. I'm going to increase it 400 pounds. Okay, so it's currently 200 pounds, but I'm going to keep the gas out from getting in the pump. Right? And so I'm going to crank up the tubing pressure from 200 to 600 pounds. Now, increasing the tubing pressure here at surface does not stop gas from getting in the pump. but I've heard this many times from pumpers, okay? So it wouldn't be uncommon to maybe have a pumper tell you that. I'm going to keep the gas out of the pump by increasing the tubing pressure. And so if he takes it from 200 to 600 psi, well, what did we do? Well, we're going to increase the pressure differential because now that additional pressure at surface is increasing our pump displacement pressure. And what's that going to do? That's going to increase our fluid load. Our fluid load is based on the pressure differential. So how much is it going to increase our fluid load? Well, if we look at this scenario here with the 1¼ inch, it's going to increase it 500 pounds. So that's an additional 500 pounds of rod loading, or that's going to contribute to rod loading. If we had an 1¾ inch, it's going to increase it 1,000 pounds. And then if we have a 2½ inch, it's going to increase it 2,000 pounds. Now notice the increase, so this was 500 pounds. Okay, this is an 1¼ inch. And if we double the diameter of the plunger, okay, should that double the increase? Okay, well, this was a 500-pound increase, but if we double the diameter to a 2½ inch, what we have here is 2,000 pounds. Well, that's 4 times as much. Now, why is it 4 times as much? Remember, when you're looking at the area of something, it's the diameter squared. And so if we double something, that would be 2 squared. That equals 4x. And so it actually, what's interesting about this illustration is that when you increase tubing pressure, it's going to have a more dramatic effect. It's going to increase your rod loading more. It's also going to increase your rod stretch more if you have a larger plunger diameter. And I've never heard anybody take this into consideration, when they're messing around with the pressure at surface on their tubing, right? It's like, hey, I'm going to increase the tubing pressure. Nobody ever says, whoa, 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 what diameter plunger does it have? Nobody talks about that, but it is actually something to take into consideration. When you have a larger cross-sectional area, it's going to create more fluid load and increasingly more rod stretch. And as we'll learn here, people think increasing tubing pressure helps the well to pump better, but if you have especially a fiberglass rod string in a larger diameter pump, let's say you have an 1¾ inch at 10,000 feet with fiberglass, as you increase that fluid load on the plunger, that's going to increase the rod stretch, and potentially you're decreasing your downhole stroke length in all likelihood. So something to keep in mind. So that is the fluid load. Understand this equation and this relationship right here, and we're going to end it off right there. And in the next video, we're going to start up with rod stretch and look at how that is generated and how that affects the system and the downhole stroke length.